Hi everyone. In this second part of the video we're going to do a number of examples involving integrals over these general regions. So let's look at this next example. So as I said in the previous example, it's a good idea to sketch these regions. So the example we're working on, I'll just split off the stuff from above. So we're now working on this example here, the double integral of the square root of y squared plus 16. Let's sketch the region that we are integrating over. So what we have is we've got x is going from 0 to y. So that means we are interested in this line y equals x. And we have y is going from 0 to 3. So if I just notch off 3 units up here, then y is going from 0 to 3. So we are interested in the region where x is trapped between 0 and y is trapped between 0 and 3. And the set of all points that satisfy those conditions are these points here. So there's our region. And now what we'd like to do is try to see if we can recognize it. Is it a vertically simple region? Is it a horizontally simple region? Well, we can recognize it as either in this case. The way I like to do this is if I want to recognize whether it's vertically simple, I just imagine a bunch of vertical lines sweeping out that region. And as I sweep out that region, can I describe the position on that line segment that sits at the bottom of the region and the one that sits at the top as functions in terms of x? And the answer is yes, because it goes from y equals x up to y equals 3. And so that I can recognize as a vertically simple region. Could I recognize it as horizontally simple? Well, I would draw a horizontal line for a given y value and think, is the left-hand endpoint and the right-hand endpoint, can I write those as functions of y? And the answer is yes. The left-hand endpoint is x equals 0, and the right-hand endpoint is x equals y. So it's in both cases they're functions of y. The first one is a constant function, x is 0, and the second one is a function of y, namely x is equal to y. So I could recognize this as both vertically simple or horizontally simple. Which one should I use? I'll just remove the markings and I'll look at the integral as it's set up there. The first integral we want to compute is an integral with respect to x. So that is, we are integrating the x values as they go from 0 to y. So we are integrating horizontally. So as it's set up, that's a integral where we interpreted the region as horizontally simple. Is that the one we should do? Maybe we should rewrite it so that it's an integral over a vertically simple region. It would really depend on the integrand itself and whether as I do these integrals, the first one, the second one, whether it's possible to find antiderivatives. Let's have a look at the way it's set up here and see if we can go ahead and calculate it. So in the first case, notice that our variable of integration is x, and our integrand doesn't involve an x, so it's just a constant. So this first integral is actually very straightforward to compute because this is effectively just a constant sitting there. So the antiderivative would be x times that constant. And we are evaluating as x goes from 0 to y dy. So then evaluating at the endpoints, taking the difference, gives us y times the square root of y squared plus 16 dy. And so we're done that first integral. And so that was quite nice. Now for the second integral. Here I can recognize that a substitution could be used here. I could substitute for y squared because its derivative, which is 2y, or effectively a multiple of y, is sitting out front. So that means I can use a substitution here. In fact, we can write down exactly what it would be the antiderivative of the square root function, which would be that to the 3/2. And then I could sort of reverse engineer what does the constant in front have to be so that when I differentiate this, it gives me the integrand in the line above. Well, when I differentiate this, I get a 3/2 that comes down, and then I get a 2y that comes out from the chain rule, and so I'll need to put a 1/3 in front in order to get everything to cancel so that the derivative becomes a y, square root of y squared plus 16. And then we're looking at that as we go from 0 to 3. So you'll notice in each of these problems, in the example before and in this example, I'm focusing really on the calculus 3 concepts: the double integrals, the setting up of the region, identifying horizontal and vertically simple regions, which integral goes first. But I'm not dwelling too much on the techniques of integration because each stage we've just boiled it down to a calculus 2 problem, and you've done calculus 2 integrals of functions of a single variable a lot in the previous course. So I am not going through the details as I would if this was our first time doing integrals in for functions of a single variable. So if you're at all struggling with any of these antiderivatives, I am saying which ones we're using, so substitution rule could be used here. So that's an indication that if you're struggling with that, have a look back at substitution rule from Calculus 2, refresh your memory with it, do some examples, get familiar with those concepts again so that you can use them when you need them here. So we've got our antiderivative, and now we'll evaluate it at our endpoints. So that's going to be 1/3, 3 squared plus 16, so that's 9 plus 16, or 25 to the 3/2, and then that's minus 1/3, 0 plugged in, so that's 16 to the 3/2. And 3/2 as a power means it's just a square root followed by a cube, so that means we've got a 1/3, and then 25 to the 3/2 means it's square root of 25 is 5, and then cubed, 5 cubed is 5 times 5 is 25, times another 5 is 125, minus, and then 16 to the 3/2 is 4 cubed, or 64. And so we get a final result of 61/3. So there's our final answer. Now you may ask the question at this stage, could we switch the limits of integration? Could we do it as a vertically simple region? So let's just see, what would that look like? I'll use a different color. So vertically simple means I would, as my first integral, fix some x value, integrate over the y values over this line segment, and then subsequently let the line segment sweep out the region by integrating over the x values. So we'll call it as a y first integral. What would we get? Well, the integral would be, let's set it up. So we've got square root of y squared plus 16 dy dx. Our y values would range over from, look at the orange line segment in our picture, the lowest the y value is going to be x. The highest the y value is going to be 3. And then x would sweep out the region from 0 to 3. So that would be our integral as a y first integral. The very first thing we need to do is anti-differentiate the square root of y squared plus 16. So if I just look at that first integral, what's the antiderivative of y squared plus 16? That's hard. Trying to figure out what the antiderivative of the square root of y squared plus 16, that's a hard problem. That's a hard problem. So in this case, that first integral turns out to be quite a hard problem to solve. Whereas if we did the opposite order of integration, our very first integral was a very straightforward integral to do. It was integrating a constant. And then our subsequent integral, we ended up getting, and I'll highlight it here, we ended up getting that y in front. And that made integrating the square root function much more simpler because we could exploit the fact that there was a y out front and use a substitution to do that integral. Whereas when I look at it as a y first integral, I'm just left with that raw square root of y squared plus 16, and that's a hard problem to do. So sometimes order does make a difference, and being able to recognize which order you want to do the integrals in, because it becomes a simpler problem, is a part of the art to doing these double integrals. And so we will get practice on doing these, and these are the kinds of things you want to think about when you're doing homework problems, for example. So let's have a look at the next example. Let's find the double integral over the region R of the function x, where R is the region bounded by these parabolas. So let's sketch these regions here, or this region. So we got the parabola y equals x squared. So it's a parabola that's going to be opening up. That's our y equals x squared. And then we've got this y equals 8 minus x squared. So that's a parabola opening down, like this. It's rather a poor sketch. I want to make sure this is symmetric at least. So let's bring this out a little bit more. There we go. That looks better because I want these points to be of the same height because there's symmetry here. So that green parabola is our y equals 8 minus x squared. The region we're interested in is the region that's bounded by these parabolas. So in other words, the parabolas form the boundaries for this region. No other curve forms the boundary of this region. So there's our region. It'd be nice to know the x values of these points of intersection. So how do we find where they intersect? Well, to find the intersection, we can just set them equal to each other. X squared is equal to 8 minus x squared, or in other words, 2x squared is equal to 8, or x squared is equal to 4, or x is plus or minus 2. So that's a minus 2 and a 2. Now we want to recognize whether this region is vertically simple or horizontally simple. Again, imagine just drawing a vertical line along the region. Do I have, for a given x value, do I have a way to describe the lower point and the upper point? Yeah, the lower point is x squared, the upper point is 8 minus x squared. So this is a vertically simple region. That means if it's vertically simple, we'll integrate with respect to y first. So we'll set it up, we'll call it a y first integral. So there's our y first integral, and it's going to be the integral. Well, maybe I'll write it like this first of all. The integral over the region R of x dA. That's sort of the general way we can write the integral. Now the specifics in terms of how we are going to calculate it is we are doing a y first integral. So it's the integral of x dy dx. What are our limits of integration for y? Well, y is going from, again, I look at that red line segment I drew in my picture. The lowest, for a given x value, the lowest y is at is going to be x squared. The highest it goes to is 8 minus x squared. So that's our inner integral. And then I let that red line segment sweep out the region. So it sweeps out from the value x equals negative 2 all the way over to the value x equals 2. So there's our double integral all set up, ready to be computed. Antiderivative of x with respect to y. So this is integral with respect to y. X is a constant relative to y. So the antiderivative would be xy. That goes from x squared to 8 minus x squared dx. I'm still working on this integrand. So that becomes the integral from negative 2 to 2 of x times 8 minus x squared minus x cubed dx. I can do a little bit of simplification to that integrand. So that becomes an 8x. Then we get a minus x cubed minus another x cubed. So that's minus a 2x cubed dx. The antiderivative of that is 4x squared minus 2/4 or 1/2 x to the 4th. And that's going to be evaluated from negative 2 to 2. And so that's going to be 4 times 4 minus 1/2 of 16, or 8, minus the same thing we get when we plug negative 2 in, which is 4 times 4 minus 8. And so I get 16 minus 8, or 8 minus 8, which is 0. So our final result for this integral is 0. All right, let's have a look at the next example. We want to evaluate this function, e to the x squared, over this region. And let's get a sketch for the region. So our region is x is going to be between y over 2, so that's like a y equals 2x, so it's going to be a line that looks like this, y equals 2x, or in other words, x is equal to y over 2. And x is the square root of log 3. So there is x equals the square root of log 3. And y is going to range between the values of 0 and 2 root log 3. So we'll continue our y-axis up here. We can see that that's precisely that point right there, 2 root log 3. So what is our region? X is between the line and the root of log 3, so that means it's sitting to the right hand side of the line. And y goes from 0 all the way up to 2 root log 3. So there's our region. That's our region in blue. How are we set up with this integral? Well, we're integrating over x first. So we're integrating along x first, like this, and then along y second. So we're treating it as a horizontally simple region, or an x first integral. The problem is, when I look at that integral and I think, okay, now I want to calculate it, my very first thing I've got to do is find the antiderivative of e to the x squared. And that does not have a simple elementary antiderivative. It doesn't have an elementary antiderivative, meaning that there is no way to write its antiderivative using our known functions, our known elementary functions, exponentials, logarithms, polynomials, trig functions, and the like. So I'm stuck right at the start. Can't do this problem because I can't find an antiderivative for e to the x squared. But if we look back at a previous one, we have a glimpse of hope. If I was to look at this problem as an y first integral, I run into a problem with being able to compute it. But as soon as I looked at it as an x first integral, it became quite straightforward to compute it. And so we're going to hope that this is the case here. And in fact it is. And with these integrals, this is what you want to look for. If one way is going to be hard to solve, hard to compute because of calculating an antiderivative or what have you, then look at switching the order of integration and see if that makes the problem simpler. So that means that what I'm going to do is I'm going to remove this red indicator here because that was just how it was set up in the problem as a horizontally simple region. Instead, I'm going to take a vertical line segment like this and set my integral up. So I'm going to switch my order of integration. So switch order of integration. And the most straightforward way to do this is to do it by referring to the diagram. This is where the diagram comes in really handy. So I've drawn a vertical line segment. That means I'm thinking for a particular x value, what are my y values ranging between? So we've got an e to the x squared. We are going to integrate with respect to y as y ranges over the values from 0 up to an expression in terms of x. So what is that upper point of that red line segment? So at a given x value, the upper point is given by a y value of 2x. And then we will let x range over the values from 0 to the square root of log 3. So we've switched our order of integration. We've got our limits correct now for this y first integral. And now our very first integral that we're going to have to compute is an antiderivative of y. And that turns out to be quite straightforward to do because that's just going to be y e to the x squared. And we're going from 0 to 2x dx. So that means that this becomes the integral from 0 to root ln of 3 2x e to the x squared dx, and plugging 0 in is just 0. So now the antiderivative of this is e to the x squared, and that's from 0 to root ln of 3. And so that becomes e to the ln of 3 minus e to the 0, which is 1, or 3 minus 1, which is 2. So there is an example where, even though the integral as presented had an order in which it perhaps was suggesting to do it in, dx dy, upon second thought, upon reflection, we see that it's most easily done by switching the orders of integration. So draw the picture for the region, and then switch the order of integration with the help of that picture. All right, let's have a look at the last example. And this comes back to our first problem that we posed at the start of this lecture, and that is find the volume of the solid that lies under the plane and above this region bounded by y equals x and y equals x to the fourth. So our region looks like y equals x and y equals x to the fourth. There's the region we're interested in. There's our x-axis, our y-axis, and we'll treat it as a vertically simple region. So I always like to draw the line segment first, so that now when we set up the integral of the over the region of, what's our function in this case? Z is equal to x plus 2y, so that's going to be our function, x plus 2y. The integrals with respect to dA. Now that we're treating it as a vertically simple one, that means we're going to integrate over the y values first. Y values go from x to the fourth up to x plus 2y, and that's with respect to y. And then we're going to follow it up with the x integral. X goes from 0 up to where they intersect, and they're going to intersect at 1. So it goes from 0 to 1. So there's our x integral. And so there's the integral we have to compute. So it's going to be the integral from 0 to 1. The integral of the x plus 2y with respect to y becomes xy plus y squared from x to the fourth to x dx. That's the integral from 0 to 1 of x squared plus x squared minus x to the fifth minus x to the 8 dx, or in other words, the integral from 0 to 1 2x squared minus x to the fifth minus x to the 8 dx. And we anti-differentiate and evaluate at 1, and what we get is 2/3 minus 1/6 minus 1/9. Common denominator in this case turns out to be 18, so this would be 12/18 minus 3/18 minus 2/18, or 7/18. And so there we go. Now, just by way of contrast, you could say, what if we were to do it using an x first integral? So that is, I'm going to say, well, I fix a slice at height y, I integrate over that slice, so as x changes from y to cubed, or fourth root of y, I should say. So again, when we're doing it from this perspective, it helps if we just change how the curves are written. So x is equal to the fourth root of y. So in this case, just draw a little horizontal line here. If we wanted to do an x first integral, then the integral would be the integral of x plus 2y dx as x ranges over the values from y to the fourth root of y. In other words, from the left endpoint of that line segment to the right endpoint of that line segment. And then we want that line segment to sweep out the region. So that line segment's got to sweep out this region. It's got to go up, 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 and it's got to start from down at the bottom and sweep all the way up. So that means we are integrating over the y values from 0 to whatever the y value is of that intersection point, and that's going to be 1 as well. So that would be our x first integral. And I'll leave this for you to compute. So compute this to see we get the same answer. We will get the same answer of 7/18, but you'll notice that when you do this integral, you've got to be dealing now with the fourth root of y. So above, we dealt with the fourth power of x, but if you're going to do the integrals in the opposite order, then you're going to have to deal with the fourth root of y. And that's just the nature of if you're going to use the x variable versus the y variable. All right, so I encourage you to give that a shot. Go through the integral calculations, see that you get the same result. All right, so that's it for this part of the lecture, part 2, which we go through a bunch of examples. In the next part, we are going to just look at the properties of the double Euler integral and look at an example where we use those properties to approximate a double integral. Thanks for watching.